Okay, double angle formulas. I promise these ones are not as painful to go through as the compound angle formula identities. All right, we already know about sine A plus B, or the sine of A plus B. That is one of our compound angle formulas, so we would have sine A cos B plus cos A sine B. But what if B was equal to A? And in other words, what if we could rewrite that as sine A plus A? And we could also rewrite that as sine 2A, meaning we have a double angle. So a double angle could also be a sum of equal parts of that angle. So here we have this sine 2A, and we're going to use what we know about our compound angle formulas to create some formulas for double angles. So if we were going off of sine A plus A, and we want to use our compound angle formula, we would say sine A cos A, sine would be the same, plus cos A sine A. Sorry, just 1 second. Someone's knocking on my door. Okay, I'm back. One of our special education classes delivers coffee to teachers sometimes, so that's super nice. Anyway, okay, so sine A cos A plus cos A sine A. So when we write it like this, we just have sine A cos A, and we could rewrite this as, oh, that's not an N, sine A cos A plus sine A cos A. And if we have two of the exact same thing, then we have two of them, so we have 2 sine A cos A. And that, my friends, is the double angle. Actually, let's not write it as A plus A. Let's just write it as sine 2A. That is your double angle formula for sine. So sine 2A is equal to 2 sine A cos A, and that's it for that one. So that's super nice. Okay, so let's take a look at cos. Cos A plus A. Well, cos 2A is equal to cos A plus A. So if we were going to use our compound angle formula to expand this, we would have cos A. Now, it would be A plus A, so we would have to have minus sine A. Cos A times cos A is cos squared A, and sine A times sine A is sine squared A, and that is one of the versions of the double angle formula for cos. So we can conclude that cos 2A is equal to cos squared A minus sine squared A. Okay, so that's one. Off to the side, remember that sine squared A plus cos squared A, so different because this is subtraction, is equal to 1. And remember that we can rearrange this and say that sine squared A is equal to 1 minus cos squared A, or we could rearrange it and write that cos squared A is equal to 1 minus sine squared A. And so using these identities, we can actually develop a couple more versions of the double angle identity for cos. And so we could say this is version 1, or what if we replace the cos squared A with 1 minus sine squared A? So we could say that cos 2A is also equal to 1 minus sine squared A minus sine squared A. And we could simplify that and say 1 minus 2 sine squared A. So that is another version of the cos double angle formula. And then there is a third one for cos, and that would be if we replace sine squared A. So we would say cos squared A minus sine squared A is equal to 1 minus cos squared A. And this is all equal to cos 2A. And so we could say cos squared A, we would have to distribute that negative, minus 1 plus cos squared A. We have cos squared A over here, plus we have another cos squared A over there, so we have 2 cos squared A minus 1, and all of that is equal to cos 2A. That is your third option for double angle identities for cos. So there are 3 different versions, and just depending on what you're trying to do, if you have a situation, an identity, and you have cos 2a, and ultimately you're likely trying to get rid of cos in the expression, then you likely want to use this identity. Maybe the expression already has a positive sine squared a, so you're like, oh, if I can get a negative, or it just really depends. It's going to depend on what you're trying to do, but just know that there are 3 options and there's no like rule of when to use which one. And then we have our tan double angle formula. So we're going to go through this one, and then I want to reference the formula sheet for you guys and just see kind of what we've covered so far. So what we know about tan, of course, actually, no, we have our compound angle formula for tan. So tan 2a is the same as tan a plus a, so we can use our formula that before was tan a plus tan b divided by 1 minus tan a, tan b, but now angle b is going to be angle a. So let's just, oh, that's all attached. Move this down a little bit. All right, so we have, this is all equal to tan a, that's the first angle because it's going to be a, plus also tan a divided by 1 minus tan a and tan a. So when we do that, we have tan a plus tan a, which means we have 2 tan a's on the top. And then on the bottom, we have 1 minus tan a times tan a, which is 1 minus tan squared a. And that is your double angle identity for tan. So tan 2a is equal to 2 tan a divided by 1 minus tan 2a. So I'm just going to pull up our identity sheet. Just give me 1 second. Whoa, that's not what we wanted. Hang on. I have so many different versions of identity sheets. I think that I will settle on this one, but I'm filming this video before I have officially uploaded which identity sheet. But just to kind of go through, let's just assume we're going to be using this one. Like this is grade 11 stuff. We know our reciprocal trig identities. If not grade 11, we definitely learned at the beginning of this year. We know cosecant is 1 over sine, secant is 1 over cos, cotangent is 1 over tan. We know our quotient identities, tan is sine over cos, cotangent is cos over sine. We know our Pythagorean identities, sine squared theta plus cos squared theta is equal to 1. We also have a couple other Pythagorean identities here, which we haven't necessarily developed, and to be honest, we don't really use them, but they're on here, and just know that these are true and that they do exist. The related angle identities, this is basically putting into words what we were doing with those related acute angles. Really, that's all this is. It's just taking pi, which is your negative x-axis, and subtracting the angle to rewrite it. And then also, or taking pi and adding. So this would be like essentially your quadrant 2 angles. So pi minus an angle lands you back up in quadrant 2, and in quadrant 2, sine is positive, cos is negative, tan is negative. This would be taking your negative x-axis and adding an angle, which lands you in quadrant 3, where sine is negative, cos is negative, tan is positive. And this is taking your 2 pi, which is your positive x-axis, and when we subtract an angle from 2 pi, we end up in quadrant 4, where sine is negative, cos is positive, tan is negative, and we don't have quadrant 1 because that would just be theta. We wouldn't be, there is no related acute angle, so we don't have that written on here. And then what we have over here is that symmetry, and so we know that sine negative theta is equal to negative sine theta, cos negative theta is equal to cos theta, tan negative theta is equal to negative tan theta. So those are those function symmetry kind of identities that we developed. And then we also earlier in this unit looked at our correlated identities. We really only focus in on these 3 here, but again, there are other ones that exist. We could go through them, but really it's just accounting for the different quadrants that we are in again, and taking those different benchmarks and either adding or subtracting a consistent angle to shift essentially the function from sine to cos. But we don't use these ones as much, but they're definitely there. Then we spent all of lesson 4 going through our compound angle formulas, and there they all are. Those are the sine, cos, and then we added tan today. And then we also did our double angle formulas. So this was the first one that we worked on, was that sine 2a is equal to 2 sine a cos a. And then there's that 3 different versions for cos. Cos 2a is equal to cos squared theta, or sorry, I'm saying a, but cos 2 theta is equal to cos squared theta minus sine squared theta, or 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. So 3 different versions for our cos double angle, and then there's that tan double angle formula that we just established as well. So there are all of the identities that you need for this course. We've officially gone through them all. You do not need to recreate the development of them, and you don't need to memorize them, especially because you're taking this in an online setting, but you do need to recognize, why they exist, how we develop them, and how to implement them ultimately. So let's do just 2 practice questions before we end this lesson, where we are applying those double angle formulas. So use the double angle formula to rewrite the following. So this here could be rewritten, but I have it written this way to make it hopefully easier for us to see what's going on. But this is equivalent to sine 6x. So rather than having it written as sine 6x, I've given it to you as sine 2 times 3x, because then it's in that form of sine 2a, and so we can see that this 2 tells us that it's a double of this angle, where the angle is 3x. And so if we wanted to rewrite this, so again, we don't need to write it as that. Well, what we're going to do is rewrite it using our double angle formula. So our double angle formula for sine is that sine 2a is equal to 2 sine a cos a. And so this just becomes 2 sine 3x cos 3x, and that's it. We're done. Okay, so it's very helpful when it is already written, factored out like that. If I gave you sine 6x, and we will get to that, and said use the double angle formula, you might be like, but there's no double angle, there's only one single angle. So we would have to recognize that 6x is the double of 3x. And there we have it. So if we have cos 6x, we know that that is the same as cos 2 3x. So when we write it like that, it's more in our form cos 2a. And we also know that cos 2a has a couple different versions going on. So let's rewrite this using all 3 of them. So the first version is that cos squared a minus sine squared a is equal to cos 2a. So we could say that this is all equal to cos squared 3x minus sine squared 3x. This here, the angle, is the angle that is doubled, which is the 3x. So notice how the 6 is gone. There's no 6 in here because we're dealing with our double angle formula, and the angle that is being doubled is 3x. That's where the 6x comes from. We could also rewrite this using our second version, which is 1 minus 2 sine squared a. So we could say 1 minus 2 sine squared 3x. And then our third one is 2 cos squared a minus 1. So we could say 2 cos squared 3x minus 1. This is equivalent to this, is equivalent to this, is equivalent to this, is equivalent to this. If we took some angle x and subbed it into this, or this, or this, or this, or this, or this, or this, any of them, we would get the exact same answer. And at some point in, maybe it's at the start of our next lesson. I was going to say at some point in one of our lessons, I talk about the difference between an identity and an equation, and that essentially is that no matter what value of x we sub in, left is going to equal right every single time, versus an equation. We can solve for a solution of the equation, but it's only one, maybe specific, or two specific values that make the left equal the right. And identity is that no matter what I sub in for x, this will equal this, will equal this, will equal this, will equal this. Okay, this one's a little bit trickier, because it's not written as a double angle, but I'm asking you to use the double angle formula. So you may find it helpful to rewrite this as a double angle, but then you have to figure out, well, what doubled equals 3? Well, we know what we doubled to get to 3 is 1.5, which, if we want to leave it as a fraction, is 3 over 2x. So tan 2 times 3 over 2x, or 3 over 2x times 2, the tan of, is equal to tan 3x, and we may find that helpful to apply our double angle formula. So our double angle formula for tan is 2 tan A divided by 1 minus tan squared A. So when we go and apply this, we're just simply subbing in 2 tan 3 over 2, oh, that doesn't look like a 2. 2 tan 3 over 2x, we really don't need that second set of brackets there, divided by 1 minus tan squared 3 over 2x. Okay, so if you are asked to rewrite something using a double angle formula and you're like, well, what? It's not, I don't see like a double angle. Everything can be a double angle. We can divide anything we want by 2. It might not be pretty, but we can create a double angle and then rewrite in that manner. And then the very, very last thing, this lesson is, oh no, wait, this was video 2. I was like, oh, this lesson's actually going pretty quickly. This was the second video. All right, express the following as a single sine, cos, or tan function. And I'm not saying necessarily in this, so this is where too, like, eventually you'll have to figure out when do you have to use which ones, and you'll have to recognize that when you see something like this, 2 sine theta cos theta, that is our double angle for sine. So 2 sine A cos A is equal to sine, not cos, is equal to sine 2A. So this time when we go to rewrite it, we know it's going to be sine, and we know it's going to be double some angle, and that angle is this angle here, which is 4x. And we could simplify it one step further and say sine 8x. So sine 8x is equivalent to 2 sine 4x cos 4x. And we can also check any of these in Desmos. This one's an easy one, so let's throw that in there. Desmos graphing calculator. So what we were given, that was when we were checking our work in one of our other ones, was 2 sine 4x times cos 4x, and we think that is equivalent to sine 8x. And there we go. Okay, so they are in fact the same. The red is on top of the black. They are equivalent, which makes it an identity. For any value of x, there is no value of x I could sub into this that I wouldn't get the same answer as if I subbed it into this. So there, we've rewritten that one. Okay, so now we have 2 cos squared 5x over 2 minus 1. So this is 2 cos squared a minus 1, and that is equal to cos 2a. So when we go to rewrite this one, it's going to be cos 2, this angle here, which is 5x over 2. And when we simplify that, those cancel out, and it's actually just equal to cos 5x. So again, we could check this in Desmos. Let's just do one last one where we check it in Desmos because it's kind of fun, kind of satisfying. So this time we said we have 2 cos squared 5x over 2 minus 1, and we believe this is equivalent to cos 5x, and it is. So look at that. They are on top of one another. Okay, and then the very last one is cos squared x over 4 minus sine squared x over 4. So again, cos 2a is also cos squared A minus sine squared A. That's equal to cos 2A. And so we have cos squared x over 4. So we're going to have cos 2 x over 4. And again, we can simplify that. If we multiplied that in, we would have cos 2x over 4, which is just a half. So this is all equal to cos x over 2. Okay, so all of that is equivalent to this. All right, that is it for this lesson. For practice, finish that worksheet. I had you get started on the top half yesterday. We've now learned everything to complete the entire worksheet, top and bottom, sine, cos, and tan. And then there is more practice from lesson 2 and 3. I didn't give specific question numbers here because you could just pick and choose. Like this is really just like about fluency and competence. And so if you're like, okay, I like the double angles, I've got that, but I really need to work on those compound angle formulas or vice versa, you can pick and choose anything that you need off of page 400 to 401 or 407 to 408. That is all.